There we go. It's recording now. All right. I was on a good streak there for a while. I was recording without forgetting. So, oh well. All right, so let's do one example here before we actually go on involving factoring. So why don't we factor and simplify as much as possible. So let's say we were asked to simplify something like this. So let's say we have sine squared of y minus 1 over tangent of y times sine of y minus tangent of y. Okay. Now, you don't always have to have theta there. I know I was using theta in a lot of the problems up here, but it could be any letter. All right, it could be theta, it could be y, it could be capital A. You just have to have an angle letter there. All right, so don't get used to theta being there all the time. Okay, so do you see that in this problem, I have two types of factoring. All right, so the numerator, we can factor just like part 2 here. All right, but with slightly different numbers. And then in the denominator, we can factor like part 1, where there's a common factor. So on the top, that's a difference of sine squared and 1 squared. So I could factor the top as sine of y plus 1 and sine of y minus 1. But downstairs, there's a common factor. And hopefully we can all agree that the common factor there is tangent of y. So you factor tangent y out of both terms there, and that leaves you with sine of y minus 1. All right, and then remember when you factor, you're allowed to now cancel out common factors. So there's a common factor of sine minus 1. So what we can do there is cancel out sine minus 1 and sine minus 1. And now all we're doing is simplifying, which means just bring down what is left over. So in the numerator, sine y plus 1 remains divided by the tangent of y. All right, so that is the algebra that for the most part we will be using in tonight's lecture. All right, so it works the same exact way as regular old algebra as you've learned it before, but you just have trig terms in place of regular x's or regular y's, okay? But I think it's something you'll get used to. All right, so I'm just giving you a minute there to catch up for those that are writing or if you're thinking about it. All right, just give yourself a second to catch up mentally, physically. Okay. Okay, so remember the name of tonight's lecture is Trig Identities. So first let's define identity. Okay, so we say that two functions, f and g, are identically equal if f of x equals g of x. Now that word identically it's kind of like an extra word that you really don't need, all right? Because when things are equal, they are identically equal. So the word identically isn't necessarily needed there, but it is a particular term that we use, especially when we're doing something algebraically, where sometimes there isn't, a definitive answer like 5 or an answer like 1. All right, but if your answer is not a number, but maybe it's some expression, all right, those particular solutions we usually refer to as identities. That one expression is equivalent to another. Now, identical doesn't mean they look the same. It just means that mathematically they are the same. All right, mathematically. So they are identically equal. So then we say such an equation is called an identity. All right, and just think of the word identity being very similar to the word identical. All right, so whenever we say identity, it simply means that two expressions are equal. Okay, so what's the goal here with these? What are we going to be doing tonight? So the goal here is to use identities all right, to do algebraic substitution all right, and what will that do? All right, so when you use identities as algebraic substitution, these will simplify an expression. So which will simplify an expression. Most of the mathematics that you do, folks, especially in algebra, precalculus, trigonometry, and calculus and advanced mathematics, there's always going to involve a step where you're going to have to simplify. And it might not be one step, it might be 3 steps of simplifying. And simplifying occurs by either substituting something or combining terms. So it's a very important step to make a substitution which will simplify the expression if nothing else will do it. All right, so that's goal number 1. Goal number 2 is also going to be to show that 2 expressions are equal. So those are the goals with the identities in most mathematical situations. You either use these things to simplify or you use them to prove that 2 things are in fact the same thing. All right, so that is our definition and goal for tonight. So I'll give you a moment there to get caught up. But once we pick up here, so part A for tonight, we're going to have a part A and a part B. Part A is what we call single angle identities. And these, for the most part, are really easy because it only involves one angle variable, like theta. And then later on in the lecture, we're going to be looking at identities that involve more than one angle, such as like angle A and angle B. So we're going to be looking at how to simplify and combine terms with different angle values. Okay, so the first type of single angle identity are something we kind of already know from Monday. These are called reciprocal identities. All right, and this just goes back to the idea. So this stuff here in the little dotted box, don't copy this, but let's just review something from Monday that's going to help you understand the meaning of reciprocal identities. So remember we said that the sine of theta, right, is what? Opposite over hypotenuse. and then next to it, we put its reciprocal. And remember, cosecant is the reciprocal of sine. So we would just reverse the fraction and write hypotenuse on top and the opposite side on the bottom. All right, so that's the idea of reciprocals. So in other words, cosecant is the reciprocal of sine, right? So how else can we write that? So we would say that cosecant of theta is or equals the reciprocal of sine. So a reciprocal of sine could also be written like this. The reciprocal of sine is 1 over sine. Okay, so the reciprocal of anything is 1 over anything. It's like the reciprocal of 2 is 1 over 2. The reciprocal of 3 is 1 over 3, and so on. So the reciprocal of sine is 1 over sine. Okay, and then we also had cosine is adjacent over hypotenuse. And remember, the secant function is the reciprocal of that. Okay, so we could write down also that the secant of theta is the reciprocal of cosine, 1 over cosine. And similarly, the cotangent function is the reciprocal of the tangent function. That looks a little neater. So those are the 3 reciprocal identities. All right, and the second type of identities, they're kind of similar to these. And then we're going to do some examples where we use these to simplify and do all that fun algebra stuff. So if you like algebra, you're going to love this lesson tonight. There's a lot of great algebra. All right, the second type here are called quotient identities. All right, now quotient just means that you're dividing 2 things. All right, so remember, quotient means division. So we're dividing 2 things, and it's going to equal something. Okay, so first let me set this problem up with a triangle. So let's say we have angle theta here at the bottom, and we'll have sides A, B, and C. All right, so let's start by writing out the ratios, sine, cosine, and tangent. So the sine of theta would be the opposite side, B, divided by the hypotenuse, C. So remember, we can do SOHCAHTOA to remember these. Right? SOH means that the sine is the opposite side divided by the hypotenuse. Now the cosine, C, is the adjacent divided by the hypotenuse. So A is adjacent to the angle, so it's A divided by the hypotenuse, C. And then tangent, or TOA, means you divide opposite by adjacent, so it's B divided by A, and you get that. All right, now what we're going to do is take this information here and just do one thing. What's sine divided by cosine? So notice what I just did here. I'm dividing 2 things, which is a quotient. So we're actually proving the first quotient identity. So we know what sine and cosine are. It's these fractions right here. So sine is B over C. And on the bottom, cosine is A over C. Now you do have to remember a little fraction math to do these. So remember, when you divide 2 fractions, all right, you can divide by A over C, or remember the rule, you multiply by its reciprocal. So we're going to be multiplying by the reciprocal of the denominator, which is C over A. The C's cancel out, and we get B over A. Now, what's B over A? All right, hopefully you see it there in my diagram. B over A is tangent. All right, so we just showed an identity here that if you divide sine and cosine, it works out to the same value as what tangent would be. So our first quotient identity is that sine of theta divided by cosine of theta is the tangent theta. And the second one's very similar. If I flip it around, I'm taking the reciprocal, which will be cotangent. And there's only two of these. Also, it might be helpful. Sometimes the quotient identities are called the tangent and cotangent identities just because that's what they are. All right, so maybe a little note on the side for yourself that quotient identities are sometimes called the tangent and cotangent identities. All right, now let's do some examples. Okay, so number one, suppose you were asked to simplify the cotangent of theta times the secant of theta. Okay, so now how would you do something like this? So one little note that we want to make here is that sometimes when we're just asked to simplify, all right, it might be useful or it might be helpful to rewrite the problem using only sines and cosines. All right, so that's a little note in the margin I would make. Now, why is that? Well, think about this. There are 6 different trig functions. So when you start thinking about all the different ways you could simplify those, there's going to be a lot. So one thing you might notice up here, you notice that all the trig functions, like cosecant, is equal to something in terms of sine. Secant is equal to something in terms of cosine. Ignore this because cotangent and tangent, they're down here. Tangent and cotangent are also involving sine and cosine. So you can rewrite every trig expression using sine or cosine, or both. And that's useful because if there's 6 different trig functions, you can reduce 6 functions down to 2. And that makes the algebra much more doable and much more simple if you can reduce 6 names down to 2. So let's do this. Let me bring this up a little bit. So the first term there is cotangent. Put that in terms of sine or cosine. All right. So if you look at these, we got 2 choices for cotangent, but I won't use this. That's not a sine or a cosine. But let's use this substitution. That's cosine and sine. So the first term here, we would do cosine theta over sine theta. And then after the times sign, secant, that's one of the reciprocal identities, is 1 over cosine. All right, and then we see there's a common factor of cosine and cosine. So we can cancel those out. And then we get 1 over sine of theta. So you can write that as your answer because you just simplified. But also you might notice that up above, this is also equal to the cosecant. And do I prefer an answer? No. No. If you can make the right substitutions in the first step and simplify, all right, so that there's nothing else that you really can do to simplify, that's good enough. Sometimes you can have more than one answer. So what we just did here is established an identity. We just showed that if you multiply cotangent and secant, it's the same thing as 1 over sine. So that's what an identity is. All right, when you simplify something, whatever it equals is its identical output. All right, let's try the next one. Let's do something very similar. Let's try one like secant of theta times tangent of theta. So again, let's use this helpful note here. Can we rewrite these two terms so that they're sine and cosine, or one or the other? So like secant, well, there's only one thing that we have so far, secant's 1 over cosine. And tangent, that's one of your quotient identities. Tangent is sine over cosine. Oh, I'm sorry, I miswrote something. Sorry, I can't read. I put the answer as the second term. So it's secant times sine. Sorry. So then we have there, well, we don't need to rewrite sine because it's already in terms of sine or cosine. So this doesn't need to change, but the first term should, because that's not a sine or a cosine. Now what's this? This becomes sine over cosine, which is, do you recognize sine over cosine? It's tangent. That was my mistake a minute ago. I put the answer as the second term. Okay, number 3. We're going to do the same exact thing, but this time the directions are going to sound different, but it means do the same thing. Simplify and get an answer. But number 3 is asking you for a specific answer. Simplify until you get a specific answer. And it's worded weirdly. It will be worded like, establish the identity that cosecant of theta times cosine of theta is cotangent of theta. So number 2, if we were to reword the directions here, number 2 was originally simplify. And I didn't give you an answer. We just had to simplify till we got something different. So if we were to reword number 2 using this language, number 2 could be reworded as, establish the identity that secant of theta times sine of theta is equal to the tangent of theta. So it's the same type of problem, it's just worded differently, but this has to be your answer, okay? So in other words, we simplify this, and this is our answer. So in other words, we're going to simplify only the left side. So let's bring that down. Cosecant of theta times cosine of theta. All right, so let's use the rule there. We rewrite everything in terms of sine and cosine. So the first term is not sine or cosine, but we can pick it out of the list from above. It's 1 over sine. This term here is already a cosine. Don't change it to something else. Leave it as cosine. All right, remember that's cosine over 1. So when you combine these, you get cosine over sine. Okay, and then cosine over sine is right up here, right in that box. Cosine over sine is cotangent, which is what we wish to show, right? This is the answer, and that's what we got. So, voila, what we wish to show. We're going to do one more of these. Number 4, establish the identity that cotangent of theta over cosecant of theta is the cosine of theta. So tell you what, I'm going to give you, let's say, 30 seconds. So what I would like you to do is set it up and see if you can reduce it until it equals the cosine. So the cosine should be your answer. So don't use the cosine here. Use the left side and simplify it as much as you can by using substitutions from the formulas above, from the identities above. So I'm going to give you about 30 seconds to fill some stuff in and see if you can reduce it until it's cosine. If you can't, I'll show you. All right. Have you rewritten the terms in terms of sine and cosine? So the top piece, cotangent, is cosine over sine. So the numerator, I replace cotangent with its quotient identity, cosine over sine. And cosecant is 1 over sine. Now here again, we have fraction math. Fraction math. We're dividing. Now, with fractions, it's easier to change our division here to multiplying. So let's bring down the top, cosine of theta over sine. And then instead of dividing by 1 over sine, we multiply by its reciprocal, sine over 1. Now, if you do that, you can see the signs are going to cancel out. And then what's left is cosine over 1 is cosine. What we wish to show, right? Because that's what we wanted from here. Okay, so those are the first two types of identities. Let's do now the third type, which we call the even and odd identities. All right, so the first thing I want to do is review something from algebra to first define even and odd identities. In our first week of class, I was going to teach you about even and odd functions, but I just ran out of time. So there's not much to really learn about these, but they are useful in trigonometry especially. So we're going to learn a little something now. So let's review what these are. All right, so for some, it probably is a review. You probably learned this in high school and maybe college algebra. If not, it's not that bad. So number one, let's use A instead. So A, f of x is called even if f of x and f at negative x are identical. So in other words, if you plug in a positive x value and a negative x value, they're the same. So like f of 2 and f of negative 2 will be equal. F of 1 and f of negative 1 will be equal. F of 5 and f of negative 5 will be equal. All right. And maybe you've heard the phrase even Steven. All right. Even Steven, if you haven't heard the phrase, that just means that things are the same. I think even Steven is typically used in when you're betting. So if things work out even Steven, it means that your wins and your losses are the same. Okay, so think of that as a positive x as your wins and negative x as your losses. They just end up being the same. So it's even, or I like to say even Steven, to remind you of that fact. Now, in terms of the graph, all right, f of x will have symmetry over the y-axis. So functions that are even, they have certainly the algebraic property here with x and negative x, but also when you graph functions like that, they'll always be symmetric over the y-axis. All right, and then odd, f of x is odd if f of negative x is not equal to f of x, but it's equal to the opposite of f of x. So notice here, the only difference is that there's a negative sign in front of f of x. So f at negative x isn't equal to f of x, but its opposite sign. Okay, and when that happens, f of x will have symmetry over the origin. And maybe I should illustrate what both of those look like. So if we go back to A, so a graph will have symmetry over the y-axis. So I'm going to highlight my y-axis. So a function might look something like this, like a parabola, for instance. And just remember that symmetry means that the distance from this point to that point, from the point to the line, these are the same distances. So that means this distance and that distance are equal. And where do they occur at? This x value is at positive x. This x value is at negative x. And notice they have the same height, which means they have the same y value. Whereas symmetry over the origin. And the origin is just a point. And this is what it would look like. You might have something that looks like this. You can kind of think of it as like diagonal symmetry, okay? Where it kind of reflects over the origin and flips the other way. So a better way to explain symmetry over the origin is that it's symmetry over both the x and y axes. So symmetry over the origin is actually symmetry over both axes. So if you were to take the right half and first flip it over the x-axis and then flip it over to the y-axis, you're going to land on this bottom half. Now let's point out that if I pick a positive x value, I'm up here. If I go to the negative x value, I'm down here. So that's the idea there when we talk about how f at negative x is the opposite of f of x. So notice this would have a positive y value, this would have a negative y value. So odd symmetry means opposite in value. And also, they have that symmetry over the origin. So odd, opposite, origin, all O words. All right, so what we're going to do now is just make a list of the functions, the trig functions that are even and the ones that are odd. All right, there's fewer even functions. And the ones that are even are cosine and secant. But more specifically, all right, let's write them using like f of x notation. All right, so f of x notation would look something like this. But instead of f, you would put cosine. So it'd be something like cosine of theta equals cosine of negative theta. And secant of theta would be the secant of negative theta. And the odd ones are the other four. So remember, sine, cosecant, tangent, cotangent. But we're going to write those like this. All right, where f of negative x, or sine of negative x, I'm going to use theta instead, is equal to negative f of x. So it would look just like that. And then the rest just fill in the same. So you have a cosecant of negative theta, a tangent of negative theta, and a cotangent of negative theta. And then just put the negative in front, and then it's cosecant theta, tangent theta, cotangent theta. All right, so there's not much involved with these. All right, so the examples here are really simple just by making one substitution. So example 1 is to simplify the sine of theta plus the sine of negative theta. Now, even in odd identities, they're usually easy to pick out because of the negative, right? Whenever you see a negative inside with the angle, that's always a dead giveaway that you're using an even or odd identity. So of course, find the one in the list above that matches sine of negative theta. So sine of negative theta is rewritten as minus sine of theta. So then here we would write, well, the first term just drops down. And then what happens to the sign in the middle? If you're going to write this as a minus sign, then this becomes a subtraction of sine of theta. So that's using the top odd identity. And now, of course, sine of theta minus sine of theta is 0. It's like x minus x is 0, sine minus sine is 0. All right, one more example, number 2. Let's use cosine. So cosine of theta plus cosine of negative theta. Now notice that's coming from the first set here, the evens, all right? The even-steven functions here. So hopefully the second term draws your attention. What substitution can I make for cosine of negative theta? Well, cosine of negative theta is the positive of cosine of theta. So this becomes cosine of theta plus cosine of theta. All right, and then what's that? So think of it as x plus x. X plus x is 2x. So cosine plus cosine is 2 cosine theta, not 0. Because this minus here, it drops out, right? Because of the identity up here, the cosine of negative theta is not a minus cosine. It's a positive cosine. So this term here gets added, not subtracted. Okay? All right, so now I think is a good time to start our first group work doing numbers 1, 2, 3, and 4. And these shouldn't really take you long. These are very, very short and very simple. So I'm going to give you 10 minutes to start these. Okay, so let's just take a quick gander at the problem sheet. I tried to be very nice in setting up the problems for tonight because I know these are a little intense, especially as you go further down the list of problems. They do get a little intense. All right. But I really try to spoon feed these to you because every problem uses a different technique. So, and that's really difficult for people that aren't math experts like me. So I really like to kind of, especially because it's a lab where you're really trying to at least just practice it, I like to kind of tell you what to do in the problems. All right, so numbers 1 and 2, all you're doing is going back to the algebra review and just simplifying a little bit. So number 1 says just factor and cancel out some terms and bring down what's left over. Number 2, just do FOIL and simplify. And look, number 3 here, this is where I start telling you what identities to use. So make sure number 3, you use at least one reciprocal and or quotient identities to show that when you multiply these terms, it's going to be 1. All right, so remember, 1 will be the answer. You have to simplify these by making those substitutions to get 1. And then number 4 is very similar to our last 2 examples. Use an even or odd identity to simplify tangent of theta plus tangent of negative theta. Now, one of your classmates asked a question in the chat about memorizing the identities. Well, in this class, no, just because everything you do will be at home, so you don't have to memorize them. If you were in a classroom with me, you still would not have to memorize these. I would let you use a piece of paper with all the identities. Okay? In fact, let me show you. Let me show you real quick. Here we go. I'm going to share with you the list of formulas that are all of the identities. And I will actually post this in Canvas. So look what we did here. So far tonight, we did the reciprocal identities, and we did the quotient identities, and we did the even and odd identities. We've done that much so far. All right, this isn't on Canvas yet, but it will be on Canvas. But the ones I starred, I think that those are the ones that will most definitely be used in calculus. And I know that because I've taught calculus in the past at other schools. And these are necessary for calculus. So, and you notice here this whole list of functions. These are all identities. You won't be learning all of these tonight, but we'll be doing a very good portion of these. And the ones that are starred, you will probably see again in calculus. All right, and you see the list here? This is the reason why I don't make you memorize these. There's too many. There's too many. And honestly, I'll be totally honest with you. The ones at the bottom, like these right here, I don't know them. I don't have them memorized. I could figure them out. I could work with them. I could simplify them, but I don't have them memorized. So I don't expect you to memorize any of these either. One other thing I will also say about memorization is this. So just pay careful attention to this. When you move on to calculus, if you take calculus at Collin College, all right, you are allowed to use a calculator. And some professors will let you use either your notes. Some will let you use a sheet of paper, like a cheat sheet when you take an exam, so that you can remember things like those formulas. However, I know for a fact that if you take calculus at UTD, most of those classes do not let you use calculators, and they do not let you use cheat sheets. They expect you to have everything memorized. So just think about that. If you decide to take calculus at a different school, there's different policies everywhere you go. Some expect you to have everything memorized, and others let you use calculators. Others don't let you use calculators. Some let you use cheat sheets, others do not. So just keep that in mind for future reference, okay? All right, now let's do our group work. We're going to do 10 minutes. I'm going to set that up right now. All right, I will see you all in 10 minutes. And share my screen with you. Oh, one other thing I want to say is that I just a minute ago I posted that handout that I showed you. It is now on Canvas, the handout with the Trig identity formulas. So that's there for you, and feel free to use it to your advantage. And also save it for calculus. I guarantee you, you're going to need it, and it will save your life when you need the trig stuff in calculus. All right, so now let's continue here with our fourth set of identities. These are called the Pythagorean identities. Now, these are called the Pythagorean identities because they're based right off of the Pythagorean theorem. So what I would like to do is prove one of the identities, and then I'll give you the other two. All right, so let's consider a right triangle. Let's put our angle theta here that we will use as a reference. And we'll have side A, B, and C. Okay, so for this particular triangle, we know that the Pythagorean theorem tells us that a squared plus b squared equals c squared. All right, side squared plus side squared is the hypotenuse squared. And c is the hypotenuse in this problem. All right, now, that's not the Pythagorean identity. That's the Pythagorean theorem. So now, one other thing we're going to write out is the sine and the cosine of theta. So using the triangle here, what ratio is sine? Well, it's opposite over hypotenuse. So in this case, it's A divided by C. And then for the cosine, it's the adjacent divided by the hypotenuse. So that's side B divided by hypotenuse C. All right, so now what we want to do here is find what is the sine squared plus cosine squared. Now, some of you already know the answer to this, all right, but I'm showing you how to get the famous answer of what sine squared and cosine squared add up to. All right, so what we're going to do, we're going to take these expressions here that we just found, A over C and B over C, and we want to square them because it's sine squared, cosine squared. So right here, we're going to put A over C and square it. And right here, we're going to put B over C and square it. Now that's A squared over C squared plus B squared over C squared, just by squaring everything in the parentheses. All right, next I'm going to add these fractions together. To add fractions, you need the same denominator, right? The common denominator. And the denominator is the same for both. So it's C squared. And then we're going to add the numerators. So we add A squared plus B squared. All right, so now at this point, we're going to make our last substitution. So we already made a substitution for cosine. We made a substitution for sine in the very first step by squaring them and adding them. Now we're going to make a substitution up here. All right, so let's make a substitution for A squared plus B squared, which is our numerator. A squared plus B squared is C squared. So now we can rewrite the top as C squared over C squared, which is 1. So our first Pythagorean identity is sine squared of theta plus cosine squared of theta equals 1. And I can tell you right now that in calculus, this will be the most commonly used one, give or take. But you will see that pop up a number of times in calculus. You'll see it in physics. So if any of those classes are in your near future, you will see this identity pop up over and over and over. All right, now there's two others that come from doing similar work like this. Okay, so another one that we could get is 1 plus tangent squared is equal to the secant squared. And another one you could get is cotangent squared of theta plus 1 equals cosecant squared of theta. All right, so there's 3 altogether. And if I were to put these in order of preference, of which ones you really need to know more or the most, I would definitely say the first one is the most preferred one that you should remember. And it's not hard to memorize that one if you say it 5 or 10 times, right? Sine squared plus cosine squared equals 1, right? It's 1, right? The next one is probably second important. So it might be worth memorizing that as well. And the third one, I don't want to say it's not important because it might come up every now and then in calculus, but really you're going to see the first one more than any. Okay. So what we could do is maybe we'll use the triangle over here and just show that 1 plus tangent squared is the secant squared just by using the sides of the triangle. Let's do that. All right, so let's do that for a fun little exercise. So let's show the second one. 1 plus tangent squared of theta, show that it equals the secant squared. So remember with these identities, this is what we're going to simplify. And this over here will be our answer. So the answer you leave alone, don't do anything with it. All right, now from the triangle, the tangent ratio, so like up here in the triangle, the tangent, remember, is opposite over adjacent, right? So when we do SOHCAHTOA, that would be A over B, right? Side A over side B. Now, even though I just said we're not going to do anything with the answer, it might be helpful to think about what your answer should look like from the triangle. What is the secant from the triangle? Right? So remember, the secant's the reciprocal of cosine. So what we should see is the reciprocal of this, right? C over B. All right, but squared. All right, so we should predict that our answer is going to be C squared over B squared. All right, so we want to show that down there as our answer. All right, so let's take the left side. All right, this is what we have to simplify to this. So 1 plus tangent squared of theta will be 1 plus, what are we squaring? We're squaring that tangent ratio A over B. So that gives us 1 plus A squared over B squared. I'm going to work my way across the screen here. All right, now what we're going to do here is we're going to transform the 1 into B squared over B squared. And I'm doing that so I can add it to A squared over B squared. Right? Because when you add fractions, you need a common denominator. So B squared over B squared is 1. And I purposely used B squared so I get a common denominator. So now I add the tops. So I can write it as B squared plus A squared, or A squared plus B squared over B squared. All right. And just like right up here, remember the Pythagorean theorem, A squared plus B squared? Here's A squared plus B squared again. That is C squared. Pythagorean theorem. And there we go. All right, because that's what we wish to show. We got it. I'll give you a minute there to catch up. Okay, so now what we're going to do next is we're going to do some examples where we're going to apply these 3 identities just to simplify things down a bit. All right, so keep those identities handy. So for example, number 1. All right, we want to show that the cosine squared of theta times 1 plus tangent squared of theta, show that it equals 1 by making some substitutions. Okay, well, what we could do first is, well, we know inside the parentheses is one of those identities, right? So we have 1 plus tangent squared of theta, we know is secant squared. So what we're going to do in the very first step is bring that down. So we get cosine squared of theta times secant squared of theta, right? And now you don't need the parentheses anymore. What could I do with that? So now what we can do is use the reciprocal identity. Let me put this here. No, we'll write it here. Use the reciprocal identity that secant is 1 over cosine. Okay, so then that changes the second term. Okay, now even though it's secant squared, what do you think this will be if I square it? It will be 1 over cosine squared. And then the cosines cancel, or excuse me, the cosine squared cancels. And what's left? 1. What we wish to show. All right, we have 3 more to do here. And then we're going to our 30 minutes group work / break. So number 2, let's write it out first. Tangent squared of theta times cosine squared of theta plus cotangent squared of theta times sine squared of theta. Show that it equals 1. All right, well, maybe this one is not so obvious as to how you start it, all right? Because we got to take that big left side with the tangent, cosine, cotangent, and sine squared. We got to simplify this so that it equals 1. Okay, so now if you first take a look at the left side and you compare that to these 3 identities right here, nothing stands out so obvious as to, anything matching up with these, okay? The terms are really mixed together a little differently than what you see here. Whereas in the first problem, right here in the parentheses, this was one of those identities that clearly stood out, all right? This was the second Pythagorean identity. That's clear in the parentheses. Here, it's not so clear. So like, for example, like if this tangent squared and this cotangent squared weren't there, right, then cosine squared and sine squared would add up to 1. But these can't add up to 1 if these terms are there, all right? So what we need to do is probably simplify it down a little differently. So what we're going to first do is we're going to use not the Pythagorean identity, but we're going to use quotient identities for the tangent and the cotangent. Let's get rid of those. All right, so remember the tangent quotient identity is sine over cosine, and cotangent is the reciprocal of that, cosine over sine. But remember, we're squaring it, right? So tangent squared will be sine squared over cosine squared. So let's simplify. And then next to it is a cosine squared. Plus cotangent squared. So remember, just take the expression for cotangent and square everything, right? Cosine squared and sine squared. And the next to it is a sine squared. All right. Now remember the 1, don't bring that down. Remember, that's supposed to be what the answer is. All right, so for those that are done writing, just think about what would you do next? What would you carry down and then show how that would simplify to 1? All right. Does everybody see cancellation happening here? There should be cancellation. Cosines cancel there, right? Cosine squared over cosine squared. And sine squared and sine squared cancel. And then that drops down, sine squared plus cosine squared. Now that we can say is 1 since, well, since that. Oh, that's terrible writing. All right, and that's just the first identity, the one that was starred 3 times. Remember that one? That's why it equals 1, because we showed that sine squared plus cosine squared is 1. Voila. All right, now this problem here is very similar to number 7 on your lab. All right, so pay attention. Okay, so remember that the left side is what we're going to simplify. And the right side should be your answer. So now this is where we're going to use another algebraic technique of factoring. So we're going to factor first. All right, so notice there's a common factor of secant squared. So let's start out by factoring out a secant squared of theta, which will give you secant squared of theta minus 1. All right, that's the first step. But notice we need to do something here with this problem so that eventually it changes from secants to tangents. Tangents in the answer. So we got to figure out how to do that. So can we make a substitution? Absolutely. So we go back up here. Where are they at? Here they are. All right. Secant squared is 1 plus tangent squared. So wherever you see a secant squared, replace it with 1 plus tan squared. Okay. So now we're going to let secant squared equal tan squared plus 1. And you're going to do it to both of these secant squared terms because you got 2 of them. So we're going to make this substitution twice. So we get, the first one is just secant squared. So we get tan squared plus 1 times. Now notice there's a secant squared minus 1. Bring down the minus 1. Now make the substitution for secant squared, which is tan squared plus 1. And the ones in the second parentheses cancel. So let's clean this up. So now we have tangent squared of theta plus 1 times the tangent squared in the second parentheses. And since there's only the tangent squared there, I really don't need parentheses anymore. So I can leave the second term without parentheses. Okay, so far we've used an algebraic technique of factoring. And then I used the Pythagorean substitution here for the secant squared terms. There were 2 of them. And that got rid of the 1s. And now we're going to do one more algebraic technique of distributing. So now distribute. right? So distribute tangent squared from the right side. So we get tangent squared times tangent squared is tangent to the fourth. Tangent squared times 1 plus 1, right, is plus tangent squared. What we wish to show, right? Same thing. All right, we'll start the fourth example in just a moment here as people are catching up. Okay, so let's do number 4 here. In one way, number 4 is kind of similar to number 6 in the lab. You know, the problem that we're going to do here has a denominator, but in the lab it doesn't have a denominator. But the very first term that we're going to have to simplify is this expression here. You have similar expressions in the lab for problem 6. So just keep that in mind when you're doing problem 6. You're going to be simplifying a term just like this and then combining it with other terms. So let's say that we have that minus 1 divided by sine of theta times cosine of theta. So we want to show that this will equal 2. All that lovely math will equal 2. Okay, so hopefully the first thing you're thinking about is simplifying the parentheses by squaring. But remember, what you have to do there is not square the terms, really, but you write it out twice and FOIL the problem. All right, so by squaring, we write it out twice, and then we're going to do fronts, outers, inners, and lasts to multiply all these terms together. All right, so first terms, right? Remember, sine times sine is sine squared. So sine to the 2 of theta. All right, and then the outside terms, sine times cosine. Well, those are different terms. So all you can do, remember, is just put them next to each other with a dot in the middle to signify that you multiply them. Inner terms, cosine times sine. But I'm going to write that the other way. I'm going to write it as sine times cosine. This way it has the same form as this term here. Sine cosine, sine cosine. The last terms, cosine times cosine is cosine squared, theta, minus 1, over sine times cosine again. Okay, so first a couple things. We can combine terms. We can use an identity to simplify things a little bit. So like you see here, there's a sine squared plus cosine squared. All right. If we put those together, that's one of the Pythagorean identities. All right. So we get sine squared theta plus cosine squared theta. We can move them together. Plus 2 sine cosine. Right, because you got 1 here and 1 there. So These are like terms, sine, cosine, and sine, cosine. And when you add 1 plus 1, you get 2 sine, cosine by combining like terms. And what else? Oh, the 1, minus 1, over sine, cosine. Okay, so hopefully we can remember now that whenever you see sine squared plus cosine squared, you're going to think 1. And then, of course, 1 minus 1 is going to cancel. And that's going to bring down 2 sine theta times cosine theta over sine theta cosine theta. And now I have a factored expression, and now common factors can cancel. So sine cancels out sine, cosine cancels out cosine, and all that's left is that lovely 2. What we wish to show, all right, had to equal 2. Okay, so now at this point, we're going to do our group work number 2. This will have a 30-minute time on it. This way you can take a break also. Okay, so I hope that you use some of the time to do the work. That is my expectation. All right, hopefully you don't just take the whole 30 minutes unless you really, really need to. So group work number 2, you're going to do numbers 5, 6, and 7. Okay. 5, 6, and 7. All right, about 15 seconds, I'm going to unshare my screen. So in case anybody's still writing, I want to give you time. I don't want to take it off the screen until you're really, really caught up. All right, so I'm going to pause the video. So I'm going to hit record and share my screen. Here we go. All right, so A has been completed. Let's now start part B with multiple angle identities. Now, when you get to probably Calculus 2 and Calculus 3, for those that actually will go on that far, this is more of a concept pretty much for Calc 2 and Calc 3. And one of the things that you'll be doing in Calc 2 and Calc 3 is working with expressions that have more than one variable. And in calculus, one of the techniques that you use to simplify multiple variables is that you try to separate those variables apart from one another. If you can separate variables from each other, then the job of solving and using the calculus techniques is so much easier. So these formulas is just one possible way of looking at multiple variables and looking at how do we separate those variables from each other. Okay, so the goal here is to separate multiple angles from each other. Because doing this helps to simplify. Multiple angles. Okay, but before we start with the formulas, we're going to be using some numerical values in the upcoming problems. And what I would like to do is just write out a little chart or table of some of these numbers. You can get these on the calculator very easily. You can check them on your own as an exercise, but we don't have to do that here. So first, let's use a table of values, a handy table of values, trig values. So we're going to use this for some of the problems. So let's say we have the angle theta. We'll have the sine of theta, the cosine of theta, and the tangent of theta. That's all we're really going to need here. So remember, you were using your calculator to get trig values the last 2 days when you were solving problems, right? This is the same idea. So, and we're going to only use it for angles of 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. That's every 90 degrees. So notice that these angles increase by 90, 90, 90, right? And also, let's put the radian equivalents, just in case the problems are written in radians. So 0 degrees is 0 radians. 90 degrees, remember, is pi over 2 radians. 180 degrees is pi radians. 270 is 3 pi over 2. And 360 is 2 pi. So we learned how to convert those yesterday. So just as a quick little reminder as to how you convert the degrees to radians, let's just take, let's take 90 degrees. So 90 degrees, convert it to radians. This is a good review from yesterday. So remember, you take the angle in degrees and you multiply it by pi over 180. Remember, pi over 180 is called the conversion factor, right? Just like you do in science classes, you multiply by a conversion factor. So now we have degrees over degrees cancel, right? And then this is pi radians, and then 90 over 180, you can reduce that, right? So 90 becomes 1, 180 becomes 2, and that's pi over 2. So that's how we get pi over 2 radians for 90 degrees. All right, now, next week, we're also going to learn a little bit more about the numbers that are in this table. So the sine of 0, I'm going to go straight down the columns. So sine of 0 degrees is 0, 90 degrees is 1, 180 degrees is 0, 270 is negative 1, 360 is 0. These are nice, easy numbers. For cosine, it's 1, 0, negative 1, 0, 1. Now remember, tangent, you don't even really need the calculator at this point. Remember, the tangent is sine divided by cosine. So if I take my sine and cosine values and divide them, I can get tangent without a calculator. So 0 divided by 1 is 0. 1 divided by 0 is undefined. 0 divided by negative 1 is 0. Negative 1 over 0 is undefined. And 0 divided by 1 is 0. Okay. So this table will come in handy for some of the problems. And granted, we could also use the calculator, but it's there when you need it. Excuse me. All right, just double check your numbers, make sure everything's correct, and we're moving on to the identities. The first type of identity in this particular section here is called the sum and difference identities. And sum and difference just means adding and subtracting. All right, and we have a couple here that we're going to be writing out. So there is a good bunch of these. All right, so the first one. If you take the cosine of the sum of two angles, So remember, these are the Greek letters alpha and beta. They represent two different angles. Okay? So alpha and beta are two angles. So this is a multiple angle formula. It's more than one angle. It's not just theta. You have an alpha and a beta. Now this is equal to, and it's not cosine alpha plus cosine beta. You would think that's what it is, but in terms of the geometry, it doesn't work out that way. Cosine of alpha plus beta is actually written as cosine of alpha times cosine of beta. And notice how they get separated into two terms. Remember, the whole idea is to separate the variables alpha and beta. Here on the left side, these are not separated, they're together. But then here they get separated, and we're not done with this. There's a little more that we have to tack on. And then it's minus sine alpha times sine beta. All right, the next one. We have the cosine of the difference of alpha and beta. And it literally just becomes the same thing, but we change the sign to a plus. You just bring down all the other terms. I'm going to put a little dashed line, because then we're going to have 2 for sine and then 2 for tangent. So the formula for sine of alpha plus beta and the sign of the difference, alpha minus beta. All right, so for the sine of alpha plus beta, it actually separates into the sine of alpha times the cosine of beta. So notice here it's sine times cosine plus the cosine of alpha times the sine of beta. Notice how the terms kind of alternate, right? First you have alpha, beta, but then it's sine, cosine, cosine, sine. But alpha, beta just stays in that order. It's like beta and alpha don't switch. Okay, and then for the next one, it's the same thing, but we put a minus sign in between. And in case you're wondering if I made a mistake, I did not. When you look at the cosines, the signs are opposite. That is correct. So with the first formula, you have a plus with a minus and a minus with a plus. But with the sine formulas, it's plus with a plus and minus with a minus. All right, so that's not a mistake in case you're wondering. All right, then we want to do tangent of alpha plus beta, which is the tangent of alpha plus the tangent of beta. That's probably what you think it would be just by separating the parentheses. But then you divide by 1 minus tangent of alpha times tangent of beta. And then when you do the difference, the plus and the minus in this equation changes to minus and plus. So we get the tangent of alpha minus the tangent of beta all over 1 plus tangent of alpha times tangent of beta. So take a minute there and just double check your writing with mine. Make sure you've copied down everything correctly and it's exactly as I have it. So I'll give you half a minute there to do that, to make sure you're caught up. Okay, let's start with our first example. So now what are we going to be doing with these formulas? Essentially, you're going to be picking out the formula that looks like it will be the most useful, right? And it's really just by matching, all right, what you see in the problem with one of these formulas here. All right, so it's really a matching game where you substitute in the one that looks most useful, and then you simplify. All right, so that's really our goal right here, is to just work these out. So number one, first we want to show that the cosine of alpha minus beta divided by sine of alpha times sine of beta will equal the cotangent of alpha times the cotangent of beta plus 1. And what I'm going to do also, I'm going to number these. 1, 2, 3, 4, 5, and 6. Okay, so in number one, remember that the left side here, this fraction, is what we're going to simplify, and then this is the answer that we are looking for. All right. So now, of course, I'm sure a lot of you are probably thinking that on the top of that fraction, that numerator, we're going to substitute in formula number 2. Right? Because that's what it looks like. Cosine of alpha minus beta, cosine of alpha minus beta. But you're going to substitute in the right side of that. So let's do that. So on the top would be the cosine of alpha, cosine of beta, plus sine alpha, sine beta. All right, so there's your first step. All right, now the next step is using a basic rule of fractions that maybe you forgot, all right, but you are allowed with fractions, you may split your numerators apart. But remember, you can't split denominators. So now we can split the numerator. And by that, I mean the first part of the numerator is the cosine pairs over the denominator, plus the second half of the numerator, the sine terms, over the denominator. Now, I'm sure everybody sees that the second half just cancels out and you get 1. Remember, when things cancel with division, you get a 1. So there's the first part. Remember, in the answer, we need a plus 1 in there, and that's what we got. Okay? Now, the next part, nothing cancels, but what we're going to do is use the fact that, remember that the cotangent is cosine over sine. All right, remember that's a quotient identity. So now we're bringing back an earlier identity to simplify 2 different cotangents that we have here. So notice we have one pair with alphas. So that's not cotangent of theta, that's the cotangent of alpha. All right, you got to use the same angle. If it says alpha, use alpha. And then this pair here, that's also a cosine over sine of beta. So that's a cotangent of beta. And there we go. What we wish to show. Okay, and this is very similar to number 10 in your lab. So just keep that in mind when you're looking for a little help in your lab. Number 1 here is like number 10 in the lab. All right, number 2. All right, actually, number 2 here will be like number 9 in the lab, FYI. Okay, so what we want to do is show that the cosine of alpha plus beta plus the cosine of alpha minus beta equals 2 cosine alpha cosine beta. All right, and remember that we start with the left side only. We're going to simplify the left side, and hopefully after simplifying it, we'll get the right side. All right, now, how many substitutions am I going to make? Well, hopefully you recognize that I'm going to have to substitute in 2 different formulas. I'll have to use formula 1 and formula 2. Okay, so formula 1, cosine of alpha plus beta is cosine of alpha cosine of beta minus sine alpha times sine beta. And then plus, oops, right, and that plus sign is this plus sign here. Okay, so that plus sign drops down. Cosine of alpha minus beta, sub it in, would be cosine of alpha cosine of beta plus sine alpha sine beta. All right, and that step is just from substituting in formulas 1 and 2 for the above terms on the left side. Now we have a bunch of terms. See if you can simplify or cancel anything. So do you see that we have a minus and a plus of sine alpha sine beta? So this minus sine alpha beta, sine alpha sine beta, and this plus sine alpha sine beta are opposites, so we can cancel them out of the equation. So then we have cosine alpha cosine beta plus cosine alpha cosine beta. These are like terms. And remember, you can add together like terms. And there's one of each. So altogether, these add up to 2 cosine alpha cosine beta. All right. So in other words, you're just thinking, if you have xy plus xy, it's 2xy. So just think of your x and y as each cosine term. All right, so this is like your 1xy. This is another xy. It adds up to 2 of those. And that was what we wish to show. All right, number 3. Let's use some of the numbers from the table from above. And we're going to use the numbers from the table to show that the cosine of pi over 2 minus theta will equal the sine of theta. All right, so which formula does this match up with? It will be 2, the cosine of alpha minus beta. And just think of the first term, that pi over 2 is your alpha, and that theta is like beta. All right, so alpha is always what's listed first, and beta is always the second angle. Okay? So now we just expand the left side, so we get cosine of pi over 2 times cosine of theta plus sine of pi over 2 sine of theta. So just remember, the formula is cosine alpha cosine beta sine alpha sine beta. But we're not using alpha and beta here. We're using pi over 2 and theta. Okay, so it's not always going to be alpha and beta. Alpha just means whatever the first angle is. Beta is whatever the second angle is. All right, and from the table, okay, we can get a number for that cosine of pi over 2 and the sine of pi over 2, right, because there's two numbers in the problem. We don't have numbers for theta, so that theta doesn't change to any value. But the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. So we substitute those in, and you get 0 times the cosine of theta plus 1 times the sine of theta. This next step here, if you can see the answer already, you could probably skip this. But in case you're not aware, 0 times cosine is 0. Cosine's gone, right? Because we multiplied it by 0. So we get 0 plus sine of theta is what we wish to show, sine of theta. Okay, number 4. Let's say we have the sine of pi over 2 minus theta. We're going to show that that equals cosine of theta. So now you want to look at which formula above that resembles. I think it's 4. Yeah, number 4. All right, for the sine of alpha minus beta. So the first angle is our alpha. So pi over 2 is alpha. Theta will be beta. And that will first expand out as the sine of alpha times the cosine of beta minus the cosine of alpha times the sine of beta. And then from the table, we can fill in two values for the sine of pi over 2. We got those already from above, so that's all right. So we make those substitutions. So here we get 1, and here we get 0. And that 1 gets multiplied to the cosine, subtracting 0 times sine. All right, remember that's the cosine when you multiply by 1. 0 times sine is 0 is cosine. All right, take a minute, get caught up. And we'll do one more and go to another group work. All right, so in number 5, we'll be showing that the tangent of the sum of pi and theta, or pi plus theta, is just the same thing as tangent of theta. So if you look at the formulas above, we'll be using the 5th one, all right, the tangent of alpha plus beta. And notice here our alpha is pi and our beta is theta. All right, so first let's use the formula to expand this. So we get the tangent of alpha, or pi, plus the tangent of beta, which is theta, all over 1 minus the tangent of pi times the tangent of beta, or theta. All right, so that's using formula 5 just to simplify or expand, really, the left side. And what do we do next? We use the table. And there's only one number that we need, and that's the tangent of pi, which is 0, which is a lovely substitution here. A very lovely substitution. So we get just use different colors here. All right, so the zeros get substituted in wherever you see tangent of pi, and it's just 0 there. And then that will equal tangent on top over 1, which is tangent of theta, which is what we wish to show. All right, so as you're getting caught up, I'll just write out what we're doing for the next group work. Group work number 3 will be 12 minutes, and you will do problems 8, 9, and 10. All right, 8, 9, and 10 will use just these formulas for the sums and differences. Okay. Yeah. So I told you that 9 and 10 relate to numbers 1 and 2. All right, so keep that in mind. Don't forget that number 1 will be like number 10. Number 2 will be like number 9. And numbers 3 and 4 will be like number 8. Okay, this way you have a little reference to look at some stuff and try to set it up and solve it successfully. Okay. I'm going to. Okay, so with this next part here, I would like to teach you a little bit about another set of multiple angle identities called the double angle identities. So to double something means to multiply it by 2. So that's what you're going to see in common in each of these identities or formulas, is that you're going to be noticing that the angle is doubled in size. Okay, so first let's write out the identities as to what these look like. So for example, sine of 2 theta. So when we say double angle, it means double the angle. All right, double theta is 2 times theta. So we have a nice little formula for this, and I'll prove this one to you. It's 2 times the sine of theta times cosine theta. Notice there's that oddball term in there, the cosine. You probably weren't expecting that because you figure this might have been 2 times sine just by bringing the 2 out. But that's not how trig terms work. You can't just bring out a number from the inside. Trig terms do not work like that. So like the sine of 3 theta is not 3 sine. All right, so that will not work. So here's the first one. Then I'm going to show you the rest of these, and I'll prove. All right, so I will show you this one. All right, once I give you the list. All right, now here is the next one. Now this next one is very interesting because it has 3 possibilities. So the cosine of 2 theta could be cosine squared theta minus sine squared theta. That's not 1. It's only 1 when there's a plus sign. So if that were cosine squared plus sine squared, then you got a 1. Okay, but there's a minus sign there, so it's not the same thing, and it's also not minus 1. Okay, what you see there is all it is. Now the cosine of 2 theta can also be written as 2 times the cosine squared theta minus 1, or it can also be written as 1 minus 2 sine squared of theta. I'll show you one of those also, how that works. Okay. And then the formula for tangent is 2 times the tangent of theta over 1 minus tangent squared of theta. All right, notice that's a square there. It's not a 2 theta. It's tangent squared of theta in the denominator. Okay, so example number 1, like I said, I'm going to prove to you how the first one is derived. So I will show you that the sine of 2 theta is simply 2 sine times cosine. All right, so we're going to start with the left side, sine of 2 theta. And what we can do with that is actually now rewrite it as the sine of theta plus theta. Because theta plus theta is 1 theta plus 1 theta is 2 theta. And now what we can do with that is use the alpha and beta formula. We could also do the sine of alpha plus beta, where alpha is theta and beta is also theta. So this is the case where alpha equals beta, and they're both theta. So if we go back to the sum and difference formulas, this is the sine of alpha plus beta, right? So that would be the sine of alpha, which is theta, times the cosine of beta, which is theta, plus, then you do the cosine of alpha, which is theta, and the sine of beta, which is theta. And you notice we have two of the same things. All right, we have a sine cosine and another sine cosine. All right, but what you just have to do is just interchange the terms of the second part. So now that they're identically like terms, and then you simply add them together. We have one of each, so altogether it's 2 times sine of theta times cosine of theta. What we wish to show. All right. So now, the point that I want to make here is that these formulas that you see here in this list, these can all be found by doing just exactly what I did in number 1 there, using the sum and difference formulas up here. So if you let all of these equal theta, okay, so for example, in the first one, cosine of theta plus theta is cosine 2 theta. So then you would have cosine theta is cosine squared, and this would be sine squared. So that's where that second identity comes from. All right, this cosine of 2 theta is cosine squared minus sine squared. That comes from the difference formula, or the sum formula for cosine of theta plus theta. Okay. All right, so let's go on and do some other problems with these. All right, so let's show that cosine to the 4th power of theta minus sine to the 4th power of theta is equal to just cosine of 2 theta. So remember, the left side is what we're going to simplify. The right side is supposed to be my answer. So what we're going to do is factor the left side. All right, and we're going to use the fact that if you factor just from basic algebra, if it were x to the fourth minus y to the fourth, this would factor into x squared minus y squared and x squared plus y squared. It's one of those differences. Okay, so doing that to the trig stuff, the cosine to the fourth minus sine to the fourth would equal cosine squared theta minus sine squared theta times cosine squared theta plus sine squared theta. All right, now, well, do you recognize the second parentheses? Do you know what that is? That's the Pythagorean theorem, or the Pythagorean identity, cosine squared plus sine squared equals 1. 1. Okay. All right, so then we get this also. Do you recognize this term here? Cosine squared minus sine squared. I'll give you a hint. It's in the box here somewhere, right in here. Cosine squared minus sine squared is exactly cosine of 2 theta. What we wish to show. Okay, let's do show that the quantity 2 times sine of 2 theta times cosecant theta squared plus 4 sine squared of theta equals 4. So again, you work with the left side and simplify it as much as we can, all right? Just by using regular algebra, maybe making a formula substitution, right? So like, for example, maybe first we could substitute in for the sine of 2 theta, right? The formula up here, right? Sine of 2 theta is 2 sine cosine. So let's substitute that in first. And, I miscopied the problem. Sorry. So I'm mixing up problems. Those 4 should have been 16s. Sorry. Okay, so now let's make the substitution now that I have the right problem. So sine of 2 theta is 2 sine theta cosine theta. And also, we're going to use the fact that cosecant is something else in the next step. Okay, so now we know cosecant of theta is 1 over sine. Now, why am I using that? So remember that when you have something that's not a sine or a cosine, right, you should try to write it in terms of sine and cosine. Because right now we have sine, cosine, and cosecant in the same problem. All right, we really want to try to reduce the number of trig terms that we have. So if it's not sine or cosine, try to put it in terms of sine or cosine. All right, so now inside the parentheses, we have 4 sine theta cosine theta times 1 over sine squared. Okay. Oh, one other thing, we don't really need the 16 and the equal sign. That's what the answer is supposed to be. I didn't really need that. You can carry it down, but. All right, now we can see here that the signs inside the brackets cancel. So then we get 4 cosine of theta squared plus 16 sine squared of theta. And then squaring the brackets, we get 4 squared is 16 cosine squared plus 16 sine squared of theta. And notice there's a common factor of 16 that we can factor out. So do that. And I hope, again, you recognize that very important expression inside the parentheses. Cosine squared times cosine squared is 1. 1 times 16 is what we wish to show, 16. So I'm going to walk through those steps one more time just to make sure that we're all clear on what it is I did. So the left side, we just had to simplify a little bit, well, not a little bit, until it equals 16. So the first thing I did was I substituted in the formula for the double angle for sine. Sine of 2 theta was 2 sine theta cosine theta. And then the next step was I wrote cosecant in terms of sine, of course, because cosecant's 1 over sine. It's the reciprocal. But then that canceled out the other sign inside the brackets. And that left me with 4 cosine of theta inside the brackets, which I then squared. So 4 squared and cosine squared is 16 cosine squared. And then the 16 sine squared just kept dropping from step to step. And finally, I factored out the 16, leaving me with another identity, the Pythagorean identity, that equals 1 times the 16. Okay? All right, now let's find a formula for the sine of 3 theta. Now, I'll tell you right now, this is like lab problem number 12. All right, in lab number 12 there, or problem number 12, you're being asked to find a formula for the cosine of 3 theta. So what you want to do is just set it up the same exact way. Terms might be a little different when you simplify it, but just do it the same exact way. Similar. So sine of 3 theta can be written as the sine of 2 theta plus 1 theta. All right, because 2 plus 1 is 3. Why am I doing that? Well, I don't have any formulas for a 3 theta, but I have formulas that involve a 2 theta and formulas that involve regular old theta. And then what I have here is an alpha and beta problem, where alpha is 2 theta and beta is the second angle, theta. All right? So now I'm going to use the sine of alpha plus beta. So remember, that was the sine of alpha cosine beta plus cosine alpha sine beta. So now for each alpha, put a 2 theta. So we get the sine of 2 theta. Cosine of beta is regular old theta. Plus the cosine of alpha, which is 2 theta, times the sine of beta, which is regular old theta. Okay, now the next thing is to make a substitution for the double angles. Okay, so that means I'm now going to replace sine of 2 theta and cosine of 2 theta. So sine of 2 theta is 2 times sine times cosine. And then I bring down the cosine that's right after it, plus now the cosine of 2 theta, remember up above, you got 3 choices. Pick your favorite. Pick your favorite, okay? All right, because they're all equal. It really doesn't matter which one you choose at this point, all right? So let's just use the first one. So you have your choice of 3, and you just pick your fave. So let's use cosine squared of theta minus sine squared of theta, multiplied by the sine of theta that comes after it. Okay, well, that should be in green, really, but. All right, and now just simplify a little bit. And what do I get? I get 2 sine of theta times cosine squared of theta plus sine of theta times cosine squared minus sine cubed of theta. All right, so these last couple terms here I got by distributing the sine of theta. So I did sine times cosine squared is this middle term, and then I have sine times sine squared. Remember, like x times x squared is x cubed, sine times sine squared is sine cubed, but there was a minus sign in front of the squared term, so that carries down. So that is my final answer. Now, of course, the question is, how do I know when to stop in a problem like this? How do I know when to stop? And you stop when your angle has coefficients of 1. All right. So the second to the last step would have been good also, but I needed to simplify the parentheses. But notice all my angles, I have 2 times the sine of 1 theta times the cosine squared of 1 theta, sine of 1 theta. I have cosine squared of 1 theta and sine cubed of 1 theta. Excuse me. And I just realized something. This is not my final answer. Anybody notice we have like terms? I didn't simplify my like terms. Notice we have a sine cosine squared, sine cosine squared. We got like terms right here. So that means it's not fully simplified. So therefore, that adds up to 3 sine of 1 theta times cosine squared of 1 theta minus the sine cubed term. Oop. There you go. Okay, so it's only simplified after you've combined all like terms. And it's only simplified when your angle theta, or whatever the letter is a 1 theta. So like up here, there was a 3 in front. So that's not simplified. In this step, there's a 2 in front of that one. That's not simplified. In this step, 2 terms have a 2 theta. That's not simplified because it needs to be 1 theta. And once you make your substitutions, then you just do some basic algebra like distributing, combining like terms, and then that will finish the problem. Okay? So when you do number 12 in the lab, make sure you do similar steps like these. They won't be exactly the same, so don't expect that because you're using cosine instead. Okay, but again, you will have similar steps involving stuff like this. And also note that for this particular problem, there's going to be more than one right answer. Just like here, when I was saying with the cosine of 2 theta, I had a choice of 3 things that I could substitute in. So really, there are 3 different answers for this particular problem alone, just because the cosine formula for 2 theta has 3 choices, and you can pick any one of them. So there's 3 possibilities for each of these problems. Okay, now, I'm not going to give you your group work yet. I'm just going to write out a few more things here. But the next lab, or the next group work, just so you know, is the last 2 problems. So our group work number 4 will be the last group work once we write down a few more things. So it'll be numbers 11 and 12. And numbers 11 and 12 are based on these formulas right up here. So as I continue on for about maybe 10 more minutes, these particular formulas, again, you'll need these for calculus, and I might put one of these on your exam tomorrow, so you might want to stick around. Okay, so a couple more sets of formulas here. We had, this was number 2, double angle identities. All right, number 3, these are called power reducing identities. And remember that in algebra, one technique that we use to simplify an expression is if there are any exponents, we try to reduce the exponents a little bit. Because remember, when you have exponents in an equation, you're going to have to factor the equation to solve it. So that makes it a little more tougher to solve when you have powers. But if you can reduce the powers so that you can eliminate them, then the solution, the simplification is a lot easier to do. And these will be very useful in Calculus 2, by the way. So if you're going on the Calc 2, these are very useful. So first, the power reducing identities, these are really just found all right, by really rearranging a little bit the double angle identities. For cosine. All right, so for example, the first one, we know that cosine of 2 theta is equal to 2 cosine squared of theta minus 1. And also, cosine of 2 theta is equal to 1 minus 2 sine squared. Of theta. And what we're going to do is solve for the squared term. So over here, we would have 2 cosine squared of theta equals, let me put the 1 first. This looks nicer. 1 plus cosine of 2 theta. So notice all I did there was I added 1 to each side. So I got 1 plus the cosine of 2 theta equals 2 cosine squared. And then dividing both sides by 2, I get this. So just remember, in Calculus 2, when you get there, all right, you may need to simplify a cosine squared term so that you can do the calculus. All right. A lot of times, a lot of calculus problems don't work well when you have exponents. But if you can make a substitution like this on the right side where there are no exponents, then the problem becomes very doable. All right. So notice that you have the left side has an exponent. The right side does not have an exponent, and they're equal. So that's a very interesting relationship here between these two quantities, is that terms with exponents and terms without exponents can be equal. So that's pretty interesting. All right, and then working this one, we get a similar expression. We get sine squared of theta equals 1 minus cosine of 2 theta over 2. We won't solve that one, but it's just, found the same way by subtracting 1 and dividing -2. It just reverses the sign there. All right, and then for tangent of, so for tangent squared of theta, so remember tangent is sine over cosine, but this is tangent squared, so it's sine squared over cosine squared. So then if we make a little substitution here, we get sine squared is 1 minus cosine of 2 theta over 2 over 1 plus cosine of 2 theta over 2. Those 2's cancel, and I get 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. All right, so again, the 2's here in each of the denominators, they just cancel out. All right, and you just end up with 1 minus over 1 plus of cosine 2 theta. Okay. Okay, so I think that's it with the formulas there. I don't think I'm going to go any further with these. But also note, the one thing I want to point out, and in case you didn't hear me earlier, I did post the list of formulas for the identities on Canvas. So this handout that I showed you earlier is now available. The one thing I want to point out before I end class here is that I also starred what's called the half angle identities. Okay, and essentially the half angle identities right here can be found essentially by taking the square roots of these, all right, and then you let your theta be replaced by theta over 2. So then this here gets divided by 2, making it a 1 theta, all right? So in other words, you're taking half of your angle quantities to get these equivalent expressions. So notice that this square root expression is very similar to these right here. If you square root these, you just get sine and cosine and tangent. And then a square root of this would be this over here. But the only difference is that you're dividing your angles by 2. So you get theta over 2, and 2 theta over 2 is 1 theta. So these half angle identities are essentially your power reducing identities with square roots, all right? They're really no different than the power reducing identities, so that's why I'm really not going to really stress these much at all. But and notice how these 3 line up, all right? They're in the same line, and remember that's because these power reducing identities came from the double angle identities, and these half angle identities come directly from the power reducing identities. Okay, so keep that in mind. Okay. All right, so there's a question here from somebody about number 9. Is there a typo in number 9? Let's see. Yeah, there's a typo in number 9, everybody. Oh, Abdullah, thank you for noticing that. Okay, so let me share my screen real quick. So in case you tried doing number 9 and you're like, why can't I solve this? It's not working out. Somebody figured out that I made a typo. All right, so let me share my screen so we can fix this. Dag nabbit. All right, so typo in number 9 on the lab. All right, so it should be, the left side is fine. Sine of alpha plus beta plus sine of alpha minus beta should equal 2 I'm trying to think if it's sine cosine or cosine sine. It's sine alpha cosine beta. All right, the typo was the this term here. All right, that it was originally sine beta. Make sure you have cosine beta. Okay. And I hope you're paying attention. I hope you're not asleep. I hope you're not wandering away from the computer. I hope you got that, because I'm going to post it in the chat, and I'll post it again on Canvas. So for those that aren't hearing this and you still have it written wrongly and you turn in the wrong solution, I will mark it wrong. All right, now, folks, one more thing before we really end class. Just a reminder that exam 3 is tomorrow, as it is Thursday. And just like the last 2 weeks, if you can turn in this lab by noon tomorrow and not a second later, you'll get +5. All right, 5 points bonus on exam 3. Okay, so bonus 5 points, all right, for turning in your Wednesday lab by noon tomorrow. Okay. All right, so the exam will be done just like the other exams. All right, just log in at 6 p.m. You'll find the questions under the exams in the assignments on Canvas. And just upload all your solutions by 10 p.m. Okay, any questions before we officially end class here? Any questions about the exam, about the lab, anything at all? This way, I'll answer those questions now in case other people were wondering those things. So it might be helpful if we just knock that out of the way.